Well, welcome everyone to the GIS Basics workshop. I'm Janet Reyes, the Geospatial Information Librarian here at UC Riverside Library. And this is a refresh and an update of a workshop I last gave a little more than 2 years ago. It's been a popular recording on our library YouTube channel, so it seems like it has struck a chord with people who are just trying to get an idea of what GIS or geographic information systems are all about. So hopefully, if you are in that situation now, seeing this workshop for the first time, you are in the right place. We'll just try to get you familiar with some of the basic concepts and the kind of things that you need to do in order to use a GIS. Like the previous one, this workshop is being recorded, and in about a week or two, we should have the recording available to you on the library's YouTube channel. If you registered for this workshop, I have your email address, and that means I can send you and will send you a PDF of the slides I'm using today. They have several useful links and things. So yeah, just watch your inbox or your junk mail box. It might go there for an email from me that will contain the slides. I have somebody assisting me today. Her name is Sally. She'll be posting messages for me in the chat and kind of helping me monitor the chat, as it's a little challenging for me to see what's going on as I'm presenting. So one of the things that she'll be posting or pasting into the chat in just a minute will be a couple of messages. One is where on the library's YouTube channel you can find our workshop recordings. And the other is for UCR affiliates only. If you're a faculty, student, or staff here at UCR, there'll be a link that we ask you to follow and just quickly enter your information in there, and that helps us track attendance for this workshop. I think that wraps up the housekeeping for now. So without any further delay, we will get started on this workshop. So here's an overview of what we'll cover today. We'll start off with some definitions about what is a GIS. Then we'll go on to what is it used for. We'll have some types of data that's used in a GIS. We'll look at some of the software options, the main software options that are out there. We'll talk a little bit about projections and coordinate systems. This is kind of a technical area, but if you don't know anything about it at all, it can really trip you up. And we don't want that. So I just want to give you some background about these things. Toward the end, we'll look at some typical first steps in using GIS, and also a new slide about AI and GIS as well will be in that section. And then finally, we'll end with just a slide with some resources for you to learn more. All right, so let's start with those definitions first of all. Every time I give a workshop like this, I kind of look around online to see if I can find definitions that really capture well what a GIS is and can do. And this time I've found two, one on the top from National Geographic. A GIS, or Geographic Information System, is a computer system for capturing, storing, checking, and displaying data related to positions on the Earth's surface. And that enables people to more easily see, analyze, and understand patterns and relationships. The one on the bottom from the US Geological Survey is a little more concise. It just says a GIS is a computer system that analyzes and displays geographically referenced information. So you notice both of these definitions have the word or a variation of the word display. And we're displaying data or we're displaying information that relates to positions on the Earth's surface. So that's very similar. Also, these definitions have the word analyze in common. Oh, down here at the bottom, it says that the system is analyzing. Up here at the top, it says a GIS enables people to analyze. So that's a little bit of a philosophical question, perhaps, but I agree with both of those. I think both the machine and the people who use it are doing some analysis there. I would just like to note that the illustration over here on the left side is supposed to convey the idea that in a GIS, you can put in multiple layers of mapped information, and you can look at them together in various combinations and see what's going on overall. And that was one of the main the ability to do that was one of the main reasons why a GIS was invented in the first place. It used to be very cumbersome with paper maps and overlays and things like that for people to do analysis about how different things on the Earth's surface intersect. So overlaying information is a very important part of the past and present and future of a GIS. So we've been talking about what is a geographic information system. Let's spend a moment thinking about what is geographic information. So there's four basic buckets, if you will, that it can be associated with. First is place names, whether it's a political type of unit, such as a nation down to a municipality, or if it's a natural feature, a mountain, an island, a particular river or water body, that kind of thing. The second category you see, I'm calling administrative units, which are just every workaday kind of areas on the ground that people who are doing jobs need to know where the boundaries are. So for instance, zip code for mailing purposes is one, school districts and service areas, those kind of things. A census tract is a way that the federal government gathers information about people in a distinct location. So all of those kind of things are also geographic information. The third type is a street address. And in modern GISs, for the most part, they have built in them the ability to recognize an address. And if you are loading maybe a spreadsheet containing addresses into a GIS, it will be able to plot points correlating to those addresses. And then finally, coordinates. So you may remember this from learning about it perhaps in geography way back when, but coordinates on the Earth's surface can be something like latitude and longitude, showing where you are in reference to the rest of the globe. If we're looking at maps that are two-dimensional, flat maps, we might have a coordinate system such as the UTM coordinates, or out here in the American West, there was a system devised a while ago that is kind of showing where property is in relation to a system that's called township, range, and section. So any of those things can be geographic information that can be used in a GIS. So now let's talk about what is a GIS used for. And I have these questions on the screen. They're not perfectly distinct questions. There's some overlap between them. And there's probably more questions that a GIS can help answer questions about, but I want you to think about things that may relate to something you're interested in or you're researching as I'm going through these types of questions, and that will maybe help you think about, this is how I could use a GIS if I really want to dive into this particular question and what I think the answer might be. So the first is location. When we use a GIS every day with Google Maps or with driving or things like that, we're interested in location, and it could be two aspects of that, right? It could be show me where all the things are that have this characteristic, like show me all the Japanese restaurants, or show me all the sightings of polar bears in Canada last year, or show me the neighborhoods where the average income is above or below a certain threshold, that kind of thing. So a GIS can help show you where those things are. On the flip side of that is like, if you want to know what features are in a particular place, like you're new in town and you just want to figure out where some of the things are that I need to go find, a map can show you that. A GIS can show you that. Now, moving on a little bit to getting a little more analytical, we can look at patterns and associations. So if you think of this thing, whatever it is, whether it's a feature that relates to the natural world or to humanity and the social sciences and things like that, however, how is that thing distributed across my area of interest? Is it just random? Is it in clumps? Is it gradually increasing or decreasing as we move from east to west or from north to south, or that kind of thing? And if it doesn't seem to be random, then, well, what else is present that might be affecting that pattern, right? So we can start to think about those kind of associations. Moving on to now, we can think about time. A GIS is known for being able to store multiple layers of data, geographic data, and that includes the same type of data, but at different time periods. So that now enables us to look at how has something changed over time, whether it was present 50 years ago and is gone now, or it's increasing a lot now, if it's spread out more than it was way back when. So all of those kind of things are something a GIS can help assess. And then finally, kind of related to the patterns and the trends, we can think about the impacts of changes for the future. So what else might change and by how much if this change occurs? And I guess these days, one of the ones we think about a lot is changes in our climate, like temperature rising, sea level rising, things like that. We're able to model what areas are going to be affected and how much and what kinds of effects they're going to be based on this one change. So we can put that into the system and it will come up with some projected answers for us. So I hope this has gotten you thinking about whatever your discipline or area of interest is, how some of these questions might pertain to what you're interested in and how a GIS might help you answer those questions. So now let's look at some of the actual things you can do with a GIS. Sometimes all you need to do is just quote unquote view maps or imagery. So I've got, of course, an aerial view of Riverside over here on the left-hand side. Well, all we're doing is looking at the satellite imagery and some of the labels of the features that are in this area. Modern GIS also has the ability, as you see at lower right, not only can you have a map, but you can have information that goes along with the map that helps explain more about what you're seeing on the map. So this is called a dashboard. And in this case, we have some bar graphs, we have some just figures, we have a couple of charts and things. And a lot of times they're interactive. So if you click on one of the things in the map, it would light up on, say, the bar chart or something like that, and vice versa. So really helps expand the amount of information you can get quickly from the map that you've created. And speaking of creating maps, sometimes that's all you need to do. So this is a very simple map, one line that I put on a Google Earth Pro session where I'm just showing the footpath that you would take to walk from one of our libraries to the other on campus here. So a map, you can add as many lines, points, or polygons to the map as you want. It could have thousands and thousands or just one like this example. And these days, we also have the ability to view data in 3D in a GIS. Comes in handy quite a bit for getting a better perspective of what we're looking at. So on the left, this is a portion of the surface of Mars. So it's not just about the Earth. We can use GIS on other planets as well. And of course, NASA is very interested in understanding the terrain of Mars, especially when they're landing spacecraft and rovers and things like that. On the right-hand side, we are back on our planet. I believe this is a portion of Singapore. And again, this is kind of not an image, but a graphical representation of the buildings and the roads and so forth on a steeply sloping area. So that, again, gives you a nice view of the mapped information in 3D. You can also create visualizations of your data. And this is just one example. So here we're looking at traffic accidents. And I don't know if you can see on your screen, but each of these hexagon stacks, there's little slices that comprise each stack. Each slice represents a point in time or a series of weeks or whatever it is. And the colors are indicating how the traffic accident frequency has been changing. So the little hexagons that are redder indicate that there have been more accidents in that slice of time. The ones that are blue over here in the upper left corner indicate that things are getting better and there's fewer traffic accidents there. So it's a very powerful way to just convey a lot of information about place and time and space and activity, all in one view. So all kinds of visualizations are possible. I just wanted to show you this one, which I think is very, very creative. So which ways The ways that we can analyze are multiple. Lots and lots of tools are available. I just want to show you some of the basics. Like I said at the beginning, the ability to overlay various types of data is super important for planners and other folks who just need to understand how different features intersect with each other. So in this example, perhaps it would be possible to calculate for a given parcel how much of that parcel is taken up in wetlands, for instance. So all kinds of combinations you can look at together or separately or in different combinations. So a very powerful capability of GIS. Now this example is kind of an old one, but I really like it because it really gets the point across. One basic thing we can do with the GIS is to create buffers around particular features that are mapped. And in this case, the student from UCLA created a map that shows for this field, which was going to be a possible sports stadium, how much of the surrounding neighborhood would be impacted by noise levels emanating from the field. So that was very clever use of the buffer tool. You can set your own distance on however far out you want it to go. It could be around other types of features as well. So buffers are very helpful for understanding what else could be impacted around a particular feature. I like this example as well. We're all kind of used to our phone being able to tell us maybe the most direct route from one place to another, but businesses definitely need some routing help as well. And this example, I believe, was a supermarket chain in the San Francisco area. Here's the distribution center. They had 4 trucks. They asked the GIS to figure out what is the most efficient routing of our 4 trucks so that together they can get to all of our stores throughout the area in a given day. So you see, this is what the GIS came up with as far as the routes that those trucks should take. And remember, I was talking a few slides ago about is the distribution of something random or is it clumped? And instead of just kind of saying, yeah, it looks like it's not random, we can use statistics to verify that, to make scientific explorations of the correlation, in this case, the correlation between 2 features. It definitely looks like there is a spatial correlation of areas that have high values and low values in each of these categories. So this is something that also a GIS can calculate for you if you're investigating that kind of thing, and many other types of analysis as well. And this slide shows you that sometimes it's not just one tool on one feature that will get you the results you need. Sometimes you have to think about multiple inputs, multiple types of tools or analysis to apply to those inputs in a particular sequence to get you the result that you want. So in this case, this is showing you the inputs and the tools that might have been used to assess potential habitat for an indigenous bird species. So models can be relatively simple or very complex, but it's not always about just doing 1 or 2 processes on a particular layer of data to get the results that you want. So I hope that has given you some ideas, again, about relating it to your particular circumstances and what you might be able to do with the GIS. I now want to talk a little bit about the types of data in a GIS. When we're thinking about spatial data, there are 2 types, vector and raster. We'll talk a little bit about each of those. Vector data has tabular data associated with it, and that is important enough that we're going to talk a little bit more in depth about that as well. So here's what vector data looks like. It is characterized by points, lines, and polygons. Polygons are another way to say shapes or areas. So this vector data is kind of mimicking what you and I would do if we were drawing a map by hand. If we had a very small feature not taking up too much space at the scale that we're looking at, we would create a little point or a dot to represent that feature. Of course, we would draw a line if we have something that's very linear, like roads or streams. And then polygons are boundaries around natural areas. It could be, income levels. It could be any kind of thing that you can think of that takes up some space on the Earth's surface. So scale does matter quite a bit when we're talking about how to represent something in vector data. For instance, if we were zoomed out and looking at the entire North American continent and we wanted to indicate where Los Angeles was, we would probably drop a point. That would be fine. But if we're zoomed into Southern California, a point is not going to depict the extent of Los Angeles, which is quite large and spread out. So in that case, the same city would be represented by a polygon rather than a point. So scale does matter when you're selecting which type of feature to draw in your vector data. So the other type of spatial data is raster, and I think we are all familiar with the concept of raster from using monitors and screens and digital images. Raster is composed of pixels. Pixels are all the same size, and each pixel is assigned a value. So this makes it very useful for imagery and also for other types of remotely sensed data, where you have a sensor that's collecting data as it passes over the landscape. It might be something like temperature or reflectance or concentration of methane or something like that in the atmosphere. So a couple of examples here on this slide. On the left, we're looking at what's called a digital elevation model, where it's a raster representation of height of the surface above sea level, say. And as you can see, each little pixel has a value assigned to it. So you really get that variation, detailed variation across the landscape that you would not necessarily get from a vector representation, which might have, maybe between 650 and 700 meters above sea level would be what the polygon represents instead of all this detailed pixel by pixel variation in the elevation in this case. On the right, this is a very old image showing you that with raster capabilities in GIS rather, you can derive maybe some classification of the features on the landscape based on the characteristics of the image. So for instance, these folks have concluded that this very, very dark signature, it represents water, and the very light signature that's linear represents a transportation feature, which is the red, and then everything else is natural land cover, and they've just left that white. So you and I would not draw a map of this area this way, but one of the benefits of raster data is that it's a very efficient way to capture some things. So yeah, it can be used for classifying images, and these days there are models that can do things like identify all the, say, parking lots in an image or all the airplanes on the ground in an image, that kind of thing. So it's gotten a lot more sophisticated, but that concept is the same, that you can pull out information from an image and reclassify it, kind of standardize it in your pixels in a raster. So we've talked about vector and raster data, which are forms of spatial data. If you are starting out using a GIS, you need some data to put into your GIS, right? So where are you going to find that data? So that's what we're talking about on this slide. Well, to start with, if you are creating the data, nobody else has done this before, then you might be drafting those points, lines, and polygons as you go along, and just you're creating this information. Similarly, if it's raster data, you can acquire it yourself, perhaps from having a camera or some other kind of sensor mounted on a UAV, which is like a drone, and you're creating that or acquiring that data yourself that way. But for a lot of us, we're going to be trying to look for existing files of vector or raster data, and here are some places where you can find them. There are many places online that are data repositories or data portals, and some of them specialize in geographic data. So sometimes you will see them refer those particular types of data repositories as geospatial data repositories or a geoportal. And these can be maintained by government agencies at all levels, from local to national. The United Nations and World Bank often have spatial data that you can download. Nonprofit organizations have host this kind of information, universities. And then the last one in this little set is a company called Esri. We'll be talking about them quite a bit more the rest of the hour. They have like the largest market share of GIS software in the world, and they have put together something they call the Living Atlas of the World, which is thousands of curated data sets that can be loaded directly into their software. So that's a great place to look for data that you don't already have. And then finally, of course, if you have coworkers and collaborators that have already created some data, you can just borrow their files from them. At the bottom of the screen, I just wanted to note that when you're looking for spatial data, what you might find is that some vector files may contain only the shapes and the basic ID. So for instance, if it's the United States, the continental United States, you would have, the polygons that represent each state and the name of the state, and that's about it. Other times you will be able to download files that contain the shapes and the basic ID, and then a bunch of what we call attribute data or information about each of those entities on the map. So just be aware that both of those scenarios are possible when you're looking for data, and there is usually something that's called metadata that tells you data information about the file that you're interested in, and that's a good place to look to understand what you'd be getting before you download it. So when you download spatial data in a vector format, a lot of times it's going to be called a shapefile. That's a very common vector data file format. It includes both the geometry and attributes for your layer of information. And the one thing that can trip you up is that when you download a shapefile, say from a geoportal, it'll be in a zip file. And you'll think, well, I just need a shapefile, so it must be one of these files inside my zip file. And look, when I open my zip file, I see something that has a suffix called SHP, so that must be my shapefile, and I don't need any of these other things because I don't know what they are. That's a very logical way to think about it, but actually the shapefile is the whole set of the files in the folder. So you're going to need all of them when you load it into your GIS. And over here on the right is some explanation about what some of the suffixes would be, what these little subfiles do for the GIS overall as you go along. So anyway, a shapefile is kind of like it sounds like a singular thing, but it's really comprised of several individual files, and you need all of them to make it work right. So it's talking about vector data. Vector data does have attributes in addition to the shapes that you see on the map. And attributes are contained in an attribute table, which gives vector information a lot of power because you can manipulate the table just like you can an Excel spreadsheet or a Google Sheet, do all kinds of analysis that way. So every row in the table corresponds to a feature on the map, and every column in the table provides a different type of information about the features. So in this example, this is an excerpt from our campus map from a while ago, and this is the parking lot data. And so you can see we have some words, we have some numbers, we have blanks. That doesn't bother it. You can have blanks, it's fine. You can also have things like URLs or a date timestamp or something like that. So all different types of data can be contained in the attribute table, but each column is going to have a consistent type of information, which is what the header indicates. This is what type of information this column refers to. So the records in the table are associated to the features on the map by an ID number that they hold in common. And on the map, you can display or analyze data in any of the columns. So possibly, like for instance, if you wanted to label these polygons, you might choose the lot ID column to create the labels for all of these polygons and so forth. And maybe you would color code these polygons based on what permit type it is, that kind of thing. So all kinds of things you can do, but that's the setup for vector data with the shape, spatial information, and then also an attribute table in the background. So sometimes you can find tabular data that has geospatial information in it, and you can associate it with a map and make a map out of that data that did not exist before. And that's a very popular thing to do. So where can you find some of this tabular data that you're going to use in your map? Well, again, if you're creating the data from scratch, you can populate the attribute table as you're creating those features. You might have field apps or surveys that are generating data as people use them as they're walking around and observing things wherever they're going. Or you could, again, find existing sources. So as I mentioned, shape files will have that tabular data in them. A CSV or an Excel or a Google Sheet can contain data, something from a database or a GPS file. But when you're finding this tabular data that you might be able to associate with some mapped data, you must have at least one field in that, one column or field in that table, whether it's coordinates, address, or some kind of identifier that will link to the records on the map or in the mapped features. So if it's not explicitly clear, that linkage is not going to work. So that's something to watch out for as you go along with this. And there's lots of sources out there that will give you more information about how to set this up. All right, I'm going to take a short pause and take a sip of water, and then we'll go on and talk about GIS software options. So this is my very unscientific classification of the different types of software that's out there. The first kind of bucket I've created I'm calling commercial, which is businesses that create GIS software as their business. And in order for you to use their software, there must be some funding exchanged so you can get the license to use it. As I mentioned earlier, Esri is a company that creates ArcGIS software. We'll talk about some of that more in just a minute, but it is very powerful software, but you generally do need to have a license set up so that you can use it. Carto is another example of a company that provides GIS software for a fee. But in the next bucket, we have open source software. So this does not require any payment. It's just available for download and off you go, or maybe it's available in the cloud. And QGIS or QGIS is one of the most popular open source softwares. We'll take a more detailed look at that in just a second as well. And then I have other, which is a very sloppy bucket, but I didn't know how else to break this down really. So my first example there is Google Earth. We all know Google is a company, and yet they allow folks to use Google Earth for free. So no payment involved there. There are other entities that have GIS software that is free with some basic functionality, but if you want to get fancier with it and use the premium option, then you'd have to pay, and Mapbox is an example of that. I've got R down here, the programming language, because it turns out that you can do things with R that mimic and sometimes even do better than what you can do with a GIS prepackaged kind of software thing. And then I've got PostGIS there, which is, if you're familiar with relational databases, it's an open source extension to PostgreSQL. So You can also do mapping and analysis kind of things with that. So lots of variation there. But let's take a look now for the next few slides about Esri. Every time I do a presentation about Esri products, I take a look at this one website where they have a list of their products, and it changes all the time. They're adding new products, they are uh, retiring old products, that kind of thing. And I know the print is very small here, but I think you might be able to make out that almost all the products have the phrase ArcGIS attached to them. So that's your clue. If you're seeing something that is an ArcGIS whatever, that is an Esri product. And I don't think I mentioned before that the headquarters of Esri is only 15 miles away from our UCR campus in Redlands, California. So very close to home for us here in Riverside. Yeah, and then there's just a whole lot of products that they have. And the two that we're going to look at the most are right up here, ArcGIS Pro and ArcGIS Online. Those are the two products that come to mind most often when people say I'm using ArcGIS. So let's take a look at that. So for ArcGIS Pro, that is something that you would install on your desktop. It runs on Windows. It does not do very well on a Mac at all, which is one drawback to using it or not using it, as the case may be. But it is very powerful. It is very developed. It has over 2,000 analytical tools and also like cartographic capabilities, all kinds of things you can do. As you see in this example, it has 3D capability. You can have multiple map windows in the same project, all kinds of things. So yeah, ArcGIS Pro is probably the most popular GIS software that's out there. And it's especially popular in the United States, in businesses and governments and that kind of thing. But ArcGIS Online is a newer product of Esri's. As the name implies, it is cloud-based. It is it's developed a lot over the last, I guess it's 15, 20 years-ish by now. When it started out, it had very few analytic tools, but now I think we're up over 200. So it can do a lot, but it can't do the 2,000 things that ArcGIS Pro does. However, because it's in the same ecosystem, what you can do is create a fairly complicated map in ArcGIS Pro and upload it to ArcGIS Online and share it out that way to the world. So that's really good. But you can also use ArcGIS Online itself. It's quite capable of making and creating overlays of existing map data. So it's getting more and more powerful as we go. And it has some pretty neat effects, and it enables you to share your work either with your own organization or with everybody in the world. So I mentioned Carto as another company that makes GIS products. I used to hear about them a lot more 10 years ago. I don't hear about them quite so much anymore. But as you can see, it's a 100% cloud native platform. And what's always struck me about Carto is the graphics. It's just really interesting graphic capabilities and the choices that you can make making maps with Carto. So QGIS, that's that open source software that I mentioned. It runs on a Mac and Windows, so that is a benefit. And it is also free, which is a good benefit too. It doesn't have a lot of, well, it has, I should take that back. It has a lot of capabilities right out of the box, but what you can do with QGIS is add what are called plugins to give it some more specialized capabilities or heavier duty capabilities than you get right out of the box, as it were. So yeah, it's a good tool, and also the shapefiles and things that you can use in ArcGIS can be brought into QGIS and vice versa. So they are compatible that way. The data that's created in one can be used in the other, which is also very good. When you download QGIS, GRASS GIS also comes with it almost all the time, or if not all the time. And GRASS is it's mainly created for using raster data. So think about natural features on the ground and things like that. That's where its strength is, as opposed to QGIS, which does both raster and vector kinds of information. This one does some vector, but its real powerhouse is in manipulating raster data. And Google Earth Pro. Google Earth Pro is a desktop application, and Google Earth for Web, which is kind of a newer feature, is also available, and they are also adding a functionality to that as time goes by. Of course, I don't know if you've ever used Google Earth Pro, but one of the features is it is globe-based, so you're pretty much always looking in 3D or have that capability very easily to do so. And you can create points, lines, and polygons in Google Earth Pro. However, it does not have an attribute table. You can create those points, lines, and polygons and save it in a file that's called either a KML or a KMZ file. And that can be translated into, say, a shapefile kind of thing. So if you have data coming from ArcGIS or QGIS into Google Earth Pro and vice versa, that can work. One of the strengths of Google Earth Pro, in my opinion, is that this little icon right here is a button for historical imagery. So you can go back, usually it's about back to the early 1980s. It'll have a variety of base map imagery that you can use. So that's great if you do need to go back in time. All right, now here's the section where I'm going to talk about projections and coordinate systems. Just again, so you have some exposure to this concept, because it could trip you up if you don't know about it. So projections refer to how do we translate what's on the curved surface of the Earth to a flat two-dimensional either print map or a computer screen, that kind of thing. If you kind of think about it for a moment, like if you had an orange or a tennis ball with stuff written on it, and then you try to flatten that all out, that's really hard. It's not something that just works super well. So smart people over the centuries have come up with different approaches to how to translate what's on the surface of the Earth to a flat surface. Here are three of them. The cylindrical version, which a Mercator projection is one that I think a lot of us are familiar with. We've all seen those maps where, say, Greenland is very, very large compared to how large it looks if you're looking at a globe. The conical projection, you've seen this if you've seen maps of the United States where the border with Canada is a curved line rather than a straight line across. And then the planar or orthographic projection, those are great for the polar regions of our globe. And there's others, but these are like three of the basic projections that are available. So if you're thinking about this at all, trying to picture this happening, you're not going to preserve all the characteristics of the features on the globe perfectly. Like something's going to get squished out, or something's going to get maybe moved a little bit in relation to other features. So in a projection, something has to be distorted. We are not going to get a perfect translation of shape and area and distance and direction. If you're a mariner, you're interested in a projection that preserves direction and distance as much as possible, because that's really important to get from a landmass to another. You want to be going in the right direction in the appropriate amount of distance. But other projections are better at preserving shape or area. And this illustration, again, it's a very old one, but it really gets the point across. When you superimpose three maps of the continental United States from three different types of projection, you get quite a variation, especially out on the fringes. So what this means for you is that if you are out there looking for different data sources and they were created in different projections, and then you bring them into a GIS, it is possible that you're going to have some things that don't line up the way they should. Now, on my next slide, I'm going to show you that it's not quite as much of a worry as it was in the early days, but it's still something to be aware of, that it can happen. So before we get to that, we need to talk about coordinate systems and datum as well. So kind of associated with the projections, coordinate systems are how you identify a particular location. There are hundreds of coordinate systems, and two basic, again, buckets of these are if it's global or spherical. So we're talking about thinking about the Earth as a globe. And if you can picture an angle created from the center of the Earth out to a particular position on the globe, the number of degrees, minutes, seconds of that angle corresponds to the latitude and longitude values that we have. Projected coordinate systems are dealing with, we've already flattened this out. Now we're on a two-dimensional surface. We know what to do. We can create a grid and we can assign numbers to that grid. And there are several hundreds probably of projected coordinate systems as well. You'll also hear the word datum as we go along with coordinate systems. The ones that we've been using in the last several years have been called NAD 83 or WGS 84. A datum pretty much relates the conceptual cylinder, as you will, or the cone that we've created in the projection to the imperfect surface of the globe. So it's a very technical kind of thing, and they're getting more and more precise over time. And in fact, some updates are coming out this year or next year. So maybe in a few years, we're not going to be talking about NAD 83 anymore. We'll have a new appellation of what datums are being commonly used. And you know what? If you have variance in different layers with different coordinate systems or different datum or different projections, in theory, that data may not line up too well. But GIS platforms these days can do what's called a reprojection on the fly. And that works fine if you're looking at the data, and that's about all you want to do. But if you're going to do analysis about, say, overlaying data or something like that, co-occurrence, the analysis results will be in doubt. But all is not lost. So GIS has tools to reconcile your layers in this regard, and you can find out more about those tools. So when it does reproject on the fly, pretty much it takes the projection that the first layer that you loaded in is in, and then it makes all the other ones match that first one. That's the method that it uses, but you can get fancy with it and change the projection of all of them if you wanted, but just make them all consistent. So that may not make a lot of sense now, but if it does come up, you'll maybe be glad that you have at least a clue of what's going on when you get that warning message on your screen. Okay, so we're going to kind of wrap up with typical first steps that you would use in using a GIS, or many of the typical first steps. And one of them is choosing a base map. You may have noticed in the examples I've shown that there are different maps in the background. Sometimes it's the satellite imagery, sometimes it's the imagery with some annotation about what's on the Earth's surface. Sometimes it's emphasizing the streets, sometimes it can emphasize the terrain, sometimes it just pretty much gives you nothing more than land versus water. So it just depends on what you need for the data you're trying to show and the point of the map that you're trying to create. At any time, as you use a GIS, you can switch out a base map. So if you decide the one that was the default or the one that you chose isn't working after all, you can switch it out and no harm done. Your data's all still going to be the same. You get to choose at any time which base map you want to have displayed. So we've been talking about adding data to your GIS, and as you do that, you might want to arrange the layers in what's called either the contents pane or the list of layers, because the order of the layers in that section of your GIS can affect what's visible. This example, again, is from the UCR campus map a while ago. This is a QGIS example, and I've put the campus boundary polygons on top. And this is like a pancake, so whatever's on top is going to obscure what's down below it. So even though all three of these layers are in there, I'm not seeing anything except the boundary for the most part. But if I just pull that boundary down below the other two, now I'm able to see the point and the other polygon features. in this map. So just something that can trip you up if you're not aware. And by the way, if you wanted to toggle on and off any of these features, usually there's a checkbox here where you could just do that. Simple to toggle them on and off if you only want to see one at a time or something. For any of the GIS platforms that you use, it is possible to change what your points, lines, or polygons look like. You do not have to create these variations on the features. They are coming out of the box. You can also change, for any of these, you could change what color they are in. In this case, this is QGIS again, and you could change the opacity. So like if there's totally transparent or totally opaque, all kinds of things, the size, the color. There's some really nice symbology here. And going back to my issue with the campus boundaries before, what I could do is change that polygon symbology just so I see the outline and everything else is hollow. And that would also have solved my problem about being able to see through to the other layers. One very popular tool that is used quite a bit in a GIS is selection. It's signified by a particular color. In ArcGIS products, it tends to be this light aqua. In QGIS, it's yellow. And this can be customized too. If you do not like these colors, you can pick something else. But anyway, when you select features, it enables you to edit the selected features. So that could be the attributes, and or it could be the shape or the position. You could even delete the feature. So if you're kind of paranoid about getting into a GIS and like, oh no, what if I delete something by accident? It's a little bit hard to do unless you already have those features selected. So just keep that in mind. For your selected features, you can then assess the attributes of those features. So it's kind of like creating a subset of that attribute table, which you can then perform different types of summarizations or analyses with. And in addition to a graphic interface where you're selecting features on the map, there's also the option of selecting features by an interface where it allows you to put in show me all the features that have this value in this column of the attribute table. So that's another way to go about selecting features by attribute rather than by location or where it is on the map in relation to something else. But it's a very powerful tool to know about. And of course, like I said, you can create features. So this is a polygon I drew in Google Earth. And as you can see, there is no attribute table, but you could add a description or a link or an image or something like that to it. But sometimes if that's all you need, that works just fine. Or you can perform analyses. And on the right-hand side here, I've got a screenshot from the tools that are available in ArcGIS Online. These are all headers that have tools underneath them. So I just expanded the summarized data one so you can get a sense of some of the tools that are available to you. Like I said, different GIS have different numbers of tools. Sometimes they call the same tool something different, all kinds of variations there, but there are tools available. Each one would open up an interface where you would select which layer you're working with, select which field or column in the attribute table you need to work with, do all that kind of customization, and then run the tool. So this is almost the last slide, and I inserted it because AI is coming. It's kind of almost here, or it kind of is here. It's going to be a bigger deal in 6 months, a year, 2 years. I'm sure the next time this workshop is given, there will be a lot more focus on AI. But for now, we just need to understand that artificial intelligence can really do quite a bit for us when it's incorporated in a GIS. It can allow for faster processing of massively large data sets. It can simplify the workflows. People can interact with the GIS using natural language. So in other words, instead of having to understand which tool does what and in which order you should use those tools, you can just type in, this is what I want to do. make it happen pretty much, and the GIS will go ahead and do it. And then another option is it will probably improve the prediction of future geospatial scenarios, which is super critical on things like maybe wildfire behavior or again, climate impacts, things like that. So it will really expand the capabilities. And some implications that are, are good too, is that it will lower the barriers to usage. So more people can use a GIS effectively without having to go through a lot of training in order to do so. It will be able to handle a lot of routine tasks, which will free up people's time for more for insights and planning. It can decrease response times to emergencies, which I think we all agree is a great thing. The faster we get out there, the better. But all of that comes with the same concerns as you've been hearing about folks having with AI in general, such as there are some ethical concerns, there's environmental impact of using AI, and so forth. So we are just right on the cusp of this really breaking out into to being a very big deal for users of GIS. We are not quite there at this present moment, though. Okay, so I'm just going to wrap up with sharing my resources slide. I have looked at all of these at least briefly, and I think they're really good. They will kind of review some of the things we've talked about today and sometimes go into more detail about some of them and sometimes expand a little bit on things that I did not touch on today. So I feel comfortable in recommending any of these to you as a way to learn more. I don't know if it made it into the chat, but we have a survey that we would like you to take about this workshop. Just takes a minute, really helps us understand if we have met your needs or what we could do better next time around. So would appreciate it if you do take that a minute just to use that link to take the survey. And with that, I thank you so much for your attention. I hope this was helpful to you. Like I said, it'll be the recording of this will be available on the library's YouTube channel in a week or two. And there's my contact information if you would like to reach out to me with further questions. Also, be aware that our library offers a lot of workshops and events. And if you are local to UCR, you are welcome to check out our library webpage and find out more about all the great events that are coming up soon. So with that, I thank you again, and we have a few minutes for any questions you might have.